So it's, of course, a great privilege to be here in beautiful Stockholm. And if you haven't done it, I totally recommend the ABBA Museum. I had the best evening of my life there, but that may say something about me. This photograph is of the campus of Cornell University. It's located in upstate New York. And this is what it looks like in the warm season, so I encourage you to visit us then. It does get a little bit chilly. So we can start. What I'm going to try and do is summarize some of the work we've done over the last few years and show how we have designed a new project that is just starting this month. So we can start by saying why wind energy, and of course there are some uncertainty bounds, but it is a massive resource. Depending upon the assumptions you make, it is many times the total primary energy supply of today. So it's also an increasing part of the electricity production mix worldwide, but also in the US and Europe. And the US has a target for 20% wind by 2030. So this installed capacity is inevitably going to rise, I would suggest. It does represent a pretty major challenge to climate science in that we have a challenge of defining the target. So whereas a lot of effort has been placed on making homogeneous temperature and precipitation records, our wind speed records are still woefully inadequate, fractured, inhomogeneous, and reanalysis products are generally relatively poor for near-surface winds. So this represents a challenge both in terms of thinking about what is the target against which we want to evaluate regional climate models, but also for statistical downscaling in terms of what are we trying to train our algorithms on. Another major challenge that it represents is that if we care about the resource, or we care about the annual electricity production, then we really need to get the upper percentiles of the wind speed distribution right. So if we look on the upper right here, a typical wind speed probability distribution is characterized by a two-parameter Weibull. So the A represents this sort of central tendency, and the K, the spread around it. So if we take a wind speed distribution like this, overlay a wind turbine power curve, so this is the amount of electrical power generated as a function of wind speed, the highly nonlinear nature of the power curve means that the red is actually showing how much power production there is as a function of wind speed. So we really need to get the mean wind speed has very little relevance to the industry, so we really need to be getting these upper percentiles correct. And I'm going to use the 90th percentile as being wind speed as being the best representation of the energy density of the wind, shown here, and of course power production. So this is a challenge in that most of our models have been developed and are evaluated predominantly on central tendency and sometimes variability around it. But really, if we don't get wind speeds right in this tail, we have lost all relevancy for the industry. If we think about operating conditions, then wind turbines, forgive me if I'm being slightly patronizing, it's not my intention, but wind turbines are not bespoke, so you get different classes of wind turbines, and you choose the one you need based on the extreme operating conditions, so the 50-year return period wind speed. So for the operating conditions, we really need to get the extremes right to choose the turbine optimally. And of course, we also need to be interested in things like icing that lead to extreme fatigue loading and can lead to turbines being shut down, that are really complex variables. So to get icing right, we would need humidity and temperature and their joint probability correct. So it's really a challenging stakeholder group. In terms of thinking about wind energy development, there are two key parameters that are used for financing. So just to give you a sense of this, unless it is a major company doing the installations such as Dong Energy in Denmark, the money has to be borrowed from an entity. The cost of that borrowing, so the interest rate, is directly related to these two parameters, the P50 annual electricity production, so this is the value that's expected to be equaled or exceeded on half of years during wind farm operation, and the P90 value, so this is the worst case where you have a 10% chance of this annual electricity production not being reached. So the greater the uncertainty in those two terms, the higher the cost of borrowing. So we can ask the question, why might climate change impact regional wind resources or operating conditions? And I'm going to make some gross simplifying assumptions here. The largest resource and currently the locations of greatest turbine deployment are within the mid-latitudes, and they are largely under the cyclone belt. So this is using Kevin Hodges' cyclone tracking detection algorithm, and wherever we see red colours here, this is showing the higher number of cyclone passages. So this is North America here, so we have a dominant track out of Colorado, and then one that sweeps essentially from Alberta across the northeast. So, of course, it means that largely our resource is being determined by synoptic scale forcing in these cyclone tracks. So if we neglect regions that have strong thermotopographic forcing of winds, we can say the resource, so the wind speeds, the 90th percentile wind speeds, are really determined by the frequency, intensity, and translational speed of transitory synoptic phenomena. So why might they change? Well, of course, the track is a function, so their location of these storm tracks is a function of the equator pole temperature gradient, temperature variance, and also critically teleconnection. So we've heard a lot about the North Atlantic Oscillation as being a driver of Northern Europe wind speeds. The translational speed is really a function of jet stream wind speeds, which again are linked to the thermal gradient. And of course, the intensity of these storms are a function of the vertical stratification and vertical momentum transport, plus of course energy from phase transition of water vapor. So at least it's plausible to say that these might change under a non-stationary global climate. So I'm trying to persuade you I haven't wasted the last 5 years of my life. The other thing that's somewhat special about the wind energy industry is that it's very nimble. So a typical deployment will last 20 to 30 years, and then in principle that site can be returned to almost greenfield conditions. So we also have to think we are interested in changes that occur in the next 30 to 50 years. Above that, the industry will just say, we'll deploy elsewhere. You know, global stilling is extremely unlikely. We'll just move our deployments to follow the storm tracks. So it means, of course, that a lot of the variability is actually dictated by internal climate modes. So I realize this is a busy diagram and I apologize for that. But what's shown here is, if we look at the NCEP-NCOR reanalysis over the last 60 years or so, and we look at when the Arctic Oscillation is in its positive phase and subtract the neutral phase, then the colours here represent the difference in wind speed at 500 millibars, 700, 850, and then 10 meters. So this is, of course, most relevant to our discussion today. But what we can see here is that when the Arctic oscillation is positive, wind speeds over this spine, so this extends into the central plains, where a lot of wind turbines are deployed, are about 1.5 meters per second higher in the 90th percentile. So this is a huge interannual signal of interannual variability. The interesting thing is the asymmetry here. If we look at the negative phase minus neutral, it is not the inverse of the positive phase. And this is, of course, because the Arctic oscillation doesn't operate in isolation, so interaction between the modes, between the Arctic oscillation and ENSO, actually mean that there's a huge asymmetry here. So, oh, I apologise, am I allowed to go back? It's awfully early, isn't it? Wherever we see white here, it means the difference is not significant. But you can see we have large areas where actually the difference is significant. So there really is an appreciable difference between wind speeds in one phase versus another. So these teleconnections, these footprints, if you like, of internal climate variability are manifest across most of the contiguous US. They're also dominant in Northern Europe. They are statistically significant, at least for the 90th percentile wind speed, and they are asymmetric due to these mode-mode interactions. And they are also an important part of climate as we move forward. So this is some work we did over this domain using HIRHAM nested in ECM5. And within this domain, what we said was in each 30-year period, so 1961 to 1990, and then moving forward, what's the likelihood of a grid cell within here moving beyond the historical norm in terms of the energy density? So this is the number of grid cells that show increasing energy density, so harnessable wind power. And you see it has a kind of if you like, an underlying periodicity here that is really strongly linked to these climate modes. So they will continue to be a very important part of wind energy variability. So of course, when we were doing this work, we had a look at how well do the CMIP5 global models do in terms of representing these key modes for North America. So this is Taylor diagrams for ENSO. This is for the North Atlantic oscillation, and then this is the Arctic oscillation, I apologize, and this is the Pacific North American pattern. And the individual dots here are the individual CMIP models. So we were computing the teleconnection indices on a daily basis and comparing those with teleconnection indices from the NCEP-NCAR reanalysis. We also have the power spectra, so this is saying, obviously, this Taylor diagrams are saying, are the modes in the right place geographically? This is saying, are they manifesting at the right time scales? So for the Pacific North American index, I would say largely so. The black line is NCEP-NCAR, the yellow line here is the ERA reanalysis product, the ECMWF product, and essentially the climate models are indistinguishable, so they are representing the patterns relatively well and their expression in the time domain, the frequency domain. That's equally true for the Arctic oscillation. It is less true, of course, for ENSO, where some models are greatly amplifying this mode that certainly is present in NCEP-NCAR, but is much, much less dominant. So as you'll see in the new project, we are using the teleconnection, the climate mode information. There is, of course, still a question of are the GCMs representing these well enough? Naturally, I wouldn't come to a regional climate modelling conference and talk to you about any global phenomena. We have also been working a little bit with thinking about this question of added value. So what's shown here are the Pryor skill scores. So we are taking each RCM for this domain, so for CONUS and the surrounding water areas, and comparing, so this is our forecast, this is our equivalent, if you like, NCEP2, so that's our baseline, and we're using the North American reanalysis as the target. So of course, if Pryor skill scores are above 0, then the regional climate models are doing a better job of representing the wind speed climate than NCEP2 does. If it's a solid dot, these are reanalysis nested RCMs. So this is the 90th percentile going up here, this is the 95th, and you can see the Pryor skill scores are strongly positive when we nest the regional models in reanalysis. The open symbols show when we nest within global climate models, and the skill certainly drops, of course, inevitably so, but there certainly is value added here, and on the basis of this, actually, we've chosen WRF to be the model we'll use in our forward work. That having been said, I do also have to kind of rip off the Band-Aid. This is the 95th percentile from NCEP2, showing the high wind speeds down here in the Central Plains and across the upper Midwest. This is where most wind turbines have been deployed. In NAR, that spatial variability is greatly suppressed. So this again is challenging, because what are we trying to evaluate our model based on? I think that there is a real problem with defining the target. What is truth? What's not shown here, but what is certainly true, is that at least for the NARCAP model, so these were run under the NARCAP project, there is great suppression of the intra-annual variability in both reanalysis and also the GCM nested runs. We looked a little bit, so this is actually from the NREL, National Renewable Energy Laboratory. It shows the wind resource, so this is what I was talking about. This is our high wind resource area. It also extends across the upper Midwest and indeed down to upstate New York here. So we also looked at this idea of, for the limited area models, when we had within NARCAP, we had 10 couples of an RCM nested in multiple GCMs, and then equally we had a smaller number of GCMs that were sampled. So there's 10 models in here, and 8 in here. So what we did was we broke down CONUS, the continental US, into these regions, the Northeast, the Midwest. And we said, okay, where you have an RCM pair that have been nested in 2 different GCMs, what's the root mean square difference in the 90th percentile from those RCMs for each region, shown in the different colors, and then the entire domain shown in gray. So if we compare this with this, we see, yes, varying the RCM does imprint more variability than varying the lateral boundary conditions, but the lateral boundary conditions are not trivial, even though, as Linda talked about on Tuesday, the domain edges were far away from CONUS, they were far out. So there's still a strong imprint in wind speeds that we think comes from the treatment of the climate modes. We had the privilege a couple of years ago with doing some work with our friends from the Rosby Center to address this idea of what's the optimal resolution if we want to get parameters that are of relevance to the wind energy community right. So they kindly allowed us access to RCA3 simulations at 50 kilometers, 25, 12.5, and 6.25. And what we wanted to ask was for things like the 50-year return period wind speed, do we, as we go up in specificity, so as we increase the resolution, do we in fact see a response in the extreme operating conditions, and how strong is that response? So we had a number of stations shown here in white that we compared the power spectra for. So again, looking in the frequency domain, are they capturing the dominant synoptic scale? Are they representing the annual variability well? But we also simply looked at, if we take this and regrid it to 50 kilometers and then average, do we get a different answer in terms of the 50-year return period wind speed? And of course we do, even though this was a hydrostatic model. So maybe I'm incorrect to say it adds value. I can say that the true 50-year return period based on data from Copenhagen is about 28 meters per second. So we were getting closer, but it was a distant target. So I think we now need to go back to this and think with the new generation of non-hydrostatic models, can we get closer to still? And I will show you one in just a second. We also think there's tremendous power in thinking about time series analysis and not looking just at the spatial domain, but actually going back and thinking about, for the grid cell that includes all bore, do we see an expression of increased variance at the right frequencies? And this, of course, shows you one of the horrors of comparing an RCM with a station, in that the 50-kilometer simulations actually show the closest agreement for the synoptic peaks. And of course it's because it had more water area. This is a coastal station. So we think there's power, but we think this is also when we need to be selecting our targets quite carefully. We have also worked quite a bit with empirical statistical downscaling, and again trying to think about the specific use case in some detail. So the wind energy industry really, at least at these timescales, doesn't really care what the wind speed is going to be on January the 1st, 2030, but they are very interested in the probability distribution. So a few years ago now, we decided that what if we were to skip the bit where we generate a time series, and we really had as our target the Weibull parameters, this scale parameter and then the shape parameter. So we developed a new technique where we say the transfer function that is linking the large-scale climate to the surface parameter of interest, let's try and do that in a way that's better tailored to the industry. So we generate two predictors here, the Weibull parameter at a given station, the scale, and also the shape parameter. And we do it as a function of the probability distribution parameters of the large-scale forcing. So the central tendency of pressure gradients within a given month, the relative vorticity, and the variance of relative vorticity. So we are trying to drive the system so that we say the statistics of the large-scale climate are well captured. We want to know the statistics of the local parameter. We don't need the day-to-day or hour-to-hour variability. So this absolutely relieves us from the need to inflate or use variance inflation on our time series. So just to give you one example of this, when we think about skill, as one of our presenters said yesterday, we should always be evaluating skill on something we didn't directly downscale. I wholeheartedly agree. So remember, we are downscaling the Weibull A and K. We're now evaluating it in terms of the 90th percentile wind speed. So of course, once you have these distribution parameters, you can calculate P90 trivially. So we took 85 stations across the eastern US, and we trained our regression equations based on 16 years of data. We withheld 5 years that were equally spaced within the 16 years, and then calculated the observed 90th percentile wind speed at the station, and that we would downscale from these equations. So of course it's not perfect. This is the one-to-one line. The scatter represents the 6 different GCM, RCM combinations here, but at least some of the spatial variability is clearly being captured. We also evaluated if we take these parameters out of a GCM, so we didn't first downscale using an RCM, do we lose any skill? So that's what's shown here in the black stars. This is just directly downscaling from the GFDL model at 200 kilometers versus placing the RegCM3 within the GFDL model, which is shown in the green stars. So essentially, if we look at our skill metrics, we're not really adding value by the hybrid downscaling, but we certainly do have some skill in representing the eastern US. Don't worry, yes, you won't need to get the hook. Just going back to the extremes, we are using a Gumbel distribution to represent the extremes, which means you can calculate the wind speed with any return period using just alpha and beta here. From the regional climate model, we used the time series of annual maxima, as we did from the station. One advantage of our downscaling approach is you can get these Gumbel distribution parameters directly from the A and K of the Weibull distribution, so it's seamless to go to the extremes. So we had the pleasure of having a really excellent time series here from northern Germany. We compared Hirham-Eckham 5 with the historical estimate of U50 and found it to be superb. Interestingly, when we statistically downscale Eckham 5, we also get even closer. Hurrah for the statisticians. So I think we have real opportunities to think about extreme winds, but really I would suggest only in synoptically dominated environments where our RCMs stand a chance of representing them, and particularly at these high, 25 kilometer resolution. So I wanted to end by introducing our new project, which is really focused on this idea of can we reduce the cost of financing. This is a bottleneck, at least in North America, for wind farm development. So our goal is very simple: better, more reliable predictions of the annual electricity production, P50 and P90, to reduce this risk. So we're taking a 3-pronged approach. One is using machine learning tools to link the climate modes to local annual electricity production. So this is kind of based on the philosophy of our empirical statistical downscaling, but it would instead use the simplest is what we're starting with, which is artificial neural networks to link daily estimates of the climate modes to develop the parameters of the distribution that we can then link to the Weibull. And we use both CMIP 5 and 6 for that. We are using limited area models. We don't have infinite supercomputing resources at Cornell, so we are only going to use WRF, but we're going to run at very high resolution, 6 or 4 kilometers, and of course link out to NA CORDEX for the larger context of the other samplings of RCMs. And then we are also going to have a go with the adaptive grid model, so the MPAS model, and this is with PNNL. Really, it's not been tested in terms of its viability, for wind climates. So the question really is, can we seamlessly generate parameters that are of interest to the wind community, or is it still a little bit of a nascent technology? And of course, all of this is being underpinned by the idea of kind of diagnostic attribution of skill, not only how well do we do, but why do we do that well? See, I'm an optimist, because why do we do that well, not why do we do that poorly? Anyway, thank you for your attention.
Okay, thank you very much, Sara. I guess first question for me is Claudia here?
Yes.
You are? Okay, so that determines how many questions we can take. So we have time for a couple really quick questions. If anyone has some? Okay, I do. So you talked a little bit about the climate change and the storm tracks, and how you looking at the synoptic variability around that, but the shift in the storm tracks is one of the most uncertain of the responses. How does that affect the enterprise of making projections for wind energy when you may be interested in the synoptic activity and not the mean storm track itself, but as you shift the storm track, the synoptic variability shifts along with it? And how does that spread then? Is the spread so wide in that the projections are not helpful, or are there ways to narrow that spread for wind energy?
I think it's a great point. At the moment, maybe this is one of the dirty little secrets, but at least in North America, they estimate annual electricity production, and then they say the P90 it represents a 20% deviation from that. And that really is just a conservative estimate. Well, they think it's a conservative estimate. So I think even though it's right when we analyse the NARCAP models, we still see quite a large spread. I think anything we can do to try and say, why is there that spread? And equally, for the independent system operators, the Northeast is one unit. So in some ways you can say, I don't mean to be trivial, but there is some tolerance for variation within the region. There's just an intolerance of a displacement out of the region. But you're right, our goal is very modest. All we said was we will better understand uncertainty. We didn't actually promise to reduce it.
Yes? To sort of one technical question is, how do you deal with the fact that most of the models store the 10-meter wind speed, whereas you probably need the 150-meter wind speed? This is a very technical question. Could you manage that, or do we have to store more wind level, let's say? And the second one is, after some year of exploitation, are the P50 and P90 forecasts verified?
Can
you repeat the question really quickly?
Oh, I'm sorry. The gentleman asked, there's a challenge. We talked about 10-meter wind speeds, but turbine hub heights are now typically 80 or 90 meters. And so, yes, we put our lowest model layer at 80 meters. So we ideally, yes, you would be like the Rossby Centre and store multiple wind levels. But yes, we store our lowest 3 levels in WRF. And then the gentleman asked, do we evaluate the P50 and P90? And yes, and you may have heard there was a wind drought in the western US this year. And yes, it did lie outside of the bounds they expected. So in the Northeast, we have not yet, within the 20 years of wind farm operation, laid outside those wind bounds. But yes, this year in the West, we did. But we also have a very nice local wind farm who are giving us their power production data, so we can do a really nice tracking of this.
Great, thank you very much.
Sorry.